All right, welcome back to the Algebraic Topology seminar. So today we are finishing up what we started last time on Van Kampen's theorem. Um, and then we're getting as far as we can, actually. We're getting as far as we can, but we're picking up where we left off with examples of Van Kampen's theorem. Um, and then we might talk about covering spaces. We might start to talk about covering spaces. Um, yeah, let's get into it. So remember, Van Kampen's theorem said that if we had a bunch of path-connected spaces that union together to make a space, then basically we can have a homomorphism that's surjective from the free group over the fundamental groups of each of these path-connected spaces. Um, into, or I guess onto, the fundamental group of the space. And that if we had a triple covering, that we could say that the kernel was this exact inclusion mapping, and rather the ideal generated by it, or the normal subgroup generated by it, and that we could get an isomorphism out of the first isomorphism theorem. So, here we're going to be talking about torus knots. So torus knots. Let the GCD of these two numbers m and n in z be 1. Um, and they're greater than 0. Um, then the torus knot k is equal to k m comma n in R3 is the image of the embedding f from S1 to the torus in R3 by z gets mapped to the pair z to the m, z to the n. So the knot k winds around the torus a total of m times in the longitudinal direction and n times in the meridional direction, as shown in the figure that I'm about to draw for cases 2, 3, and 3, 4. So example k2 comma 3, if we're given a torus, looks like wait, it goes the other direction. So let me start. No, there we go. All right. So this is the knot 2, 3, and then the knot 3, 4. would be. So this one is at least nice to draw. What? This is really confusing. Well, that looks terrible. Okay. Except I was supposed to leave a gap right in here. I'm not sure if those two lines intersect. I really don't know. They don't. I'm gonna give up on this one. Look in the book. Um, I'm not an artist. At any rate, our interest in torus knots comes from one needs to assume that M and N are relatively prime in order for the map F to be injective. Without this assumption, F would be D to 1, where D is the greatest common divisor of M and N, and the image of F would be the knot K M over D, N over D. So if MN equals D, then K MN is the same knot, and F is D to 1. One could allow negative values for M and M, but this would only change K to be a mirror image knot. Let's compute pi 1 of R3 minus the knot K. It's slightly easier to do with the calculation with R3 replaced by its 1 point compactification, the the three sphere, which is not fun. Um, so let S3 minus K be equal to the union of R3 minus K union an open ball B formed by the compactification point together with the complement of a large closed ball in R3 containing K. Um, so both B and B intersect R3 minus K are simply connected. And this is homeomorphic to S2 cross R. Since then Kampen's theorem implies an inclusion R3 minus K injects into S3 minus K. This induces an isomorphism on pi 1. So pi 1 of S3 minus K um, is computed by its deformation retraction onto a two-dimensional complex. X equals xmn, which is homeomorphic to the quotient space of a cylinder under the identification that z comma 0 is identified with e to the 2 pi I over m z comma 0, and z1 is identified with e to the 2 pi I over n z and 1. So then let xm and xn be the two halves of x formed by the quotients s1 0 to 1 half, s1 1 half to 1. Then xm and xn are the mapping cylinders. Z getting mapped to Zm and Z getting mapped to Cn. The intersection, which is identified, of course, at T is 1 half, is a circle, which is the domain end of each mapping cylinder. So xm intersect xn is s1 cross 1 half. So to obtain an embedding, so this is how it's computed, but it's gonna be a while. To obtain an embedding of x in S3 minus k as a deformation retract, we will use the standard decomposition with the 2-disk as S3 is equal to S1 with the 2-disk union the 2-disk with S1, which are two solid tori. Which is the result as regarding S3 as the boundary of the 4-disk. Like it really is an implication moving this way. Geometrically, the first solid torus can be identified with the compact region in R3 bounded by the standard torus containing K, and the second solid torus is then the closure of the complement of the first solid torus, together with the compactification point at infinity. Notice that the meridional circles in the torus bound disks in the first solid torus, while its longitudinal circles that bound disks, while it is longitudinal circles that bound disks in the second solid torus. So in the first solid torus, K intersects each of the meridian circles. Each x boundary of d squared in M equally spaced points. And what this looks like is if we have for the example with m is 3, I think those are equally spaced. We have k. Um, and so the knot looks like if this is the center point, then let me do this in a different color. Let me do this to save space. Just understand that each of those is k. We want this to be like halfway between each. And so then each k has like um these m points are separated by a union of m radical line segments, which are the orange things. Letting x vary, these radical segments then trace out a copy of the mapping cylinder xm in the first solid torus. Symmetrically, there is a copy of the other mapping cylinder xn in the second solid torus. The complement of k in the first solid torus deformation retracts onto xm by flowing within each meridian disk as shown. In similar fashion, the complement of k in the second solid torus deformation retracts onto xn. These two deformation retractions do not agree on their common domain of S1 cross S1 minus K, but this is easy to correct by distorting the flows in the two solid tori so that in the space both flows are orthogonal to the knot. After this modification, we now have a well-defined deformation retraction of S3 minus K onto X. Um, so another way of describing the situation would be to say that I'm going to write it this way. For every epsilon neighborhood, n of the knot bounded by a torus T, um, the complement S3 minus n is the mapping cylinder of T to X. So to compute pi 1 of x, we apply Van Kampen's theorem to say this is equal to pi of x1, or xm, sorry, prod pi xn. So they're both mapping cylinders that deformation retract onto circles, and the intersection of the two of them are circles, so all three of these spaces have fundamental group Z. A loop in the intersection represents a generator of pi 1 of the intersection is homotopic in XM to a loop representing M times a generator. Van Kampen's theorem says that pi of x1 is the quotient of the free group on generators A, B obtained by factoring out the normal subgroup um, generated by the element. So I guess it is also. No, I think it's mod this. I think it's mod this. I'm not entirely sure though. The way that they describe it is that this is the free group on generators A and B. B beta mod. Um, okay, so let pi1 vex mn be gmn be defined by two generators ai bj such that a to the m is equal to b to the n. If m or n is 1, if m or n is 1, then gmn is isomorphic. Um, to z. Um, since in these cases the relation just expresses one generator as the power of another. To describe the structure, um, if m and n are both greater than 1, um, let us first compute the center of the group GMN. So, and so we know that IM equals B to the N. Either one that you choose to do lies within the center because it commutes with the other. Um, and we're going to call this set C. Um, in particular, C is a normal subgroup. Um, so C is a normal subgroup of GMN. So we can pass this to the quotient group um, GMN mod C, which is the free product ZM star ZN. A free product of non-trivial groups has trivial center as a lemma. A free product of non-trivial groups has a non-trivial center. And then the implication of this is that C is equal to the center of GMN. Um, We will now show that the integers m and n are uniquely determined by the group Zm free Zn. Um, the abelianization of this is Zm Cartesian product Zn. Um, all the torsion elements of Zm free product Zn are conjugate elements, are conjugate to elements of the subgroup of subgroups Zm and Zn, hence having order dividing m or n. The maximum order of torsion elements is the larger of m and n. Hence, also, the smaller is uniquely determined since the product is well determined. The preceding analysis of pi 1 of x m n did not need the assumption that m and n are relatively prime, which was used only to relate x m n to torus knots. Um, a bonus out of this whole mess is that x22 is the Klein bottle, and that this means that it can't be embedded in R3. Um, yeah, I don't get this. I feel like we jumped around like 17 different times and said a lot of things that weren't really justified anywhere. And I still don't think that we actually computed pi 1 of S3 minus K. We computed a deformation retract from a torus to the mapping cylinder X, or to XMN. Now that is its own mapping cylinder. We never used this thing ever again. So if we have this embedding, it really seems like this would end up being pi 1 of k is equal to Zm Cartesian product Zn. Um, But it never states what pi 1 of a torus knot is. What I'm Googling this, but what is the fundamental group of a torus knot? Oh, okay. Okay. So it's not ZN, it's the free group thing. Pi 1 of S3 minus KMN is equal to, or I guess the way we did it was A and B, A, A, B, such that A to the M is equal to B to the N. And that was not clear from the text. And notably that this is obtained, so up here, this whole free group thing, this is pi 1 of K, pi 1 of S3 minus K. Since the mod equivalence here, if AM is equal to BN, then this is equal to 1, right? Because it's A to the M, A to the minus M is equal to A to the 0 is 1. And then if M or N is 1, then it's clear that this is, yeah, infinite cyclic. If they're greater than 1, I don't think any of what got written matters. And then modding out by the center does give you a free product of ZM and ZN. And then the abelianization of that is the Cartesian product. Okay, that does make more sense. It just was written down in kind of an unfriendly way. Um, this is where I would normally ask if whoever's watching, feels like they're getting it. Um, but today is Monday, and so my friends are unable to make it today. So hopefully, if you're watching this, this is not horribly confusing. And if it is, I'm sorry. So in the second example, um, the shrinking wedge of circles. Um, so consider x in R2 with x is equal to the union of circles CN, where CN has radius 1 over n with center 1 over n comma 0. And I guess this is n and n. This looks pictorially like a bunch of nested circles. Um, At first glance, one might confuse X with the wedge sum of an infinite sequence of circles, but we will show that X has a much larger fundamental group than the wedge sum. So consider the retractions Rn from X to Cn, collapsing all Ci's except Cn to the origin. Collapsing all Ci's except Cn to the origin. And if it's not clear, this is an R. That's worse. That's an R. Um, each Rn induces a surjection rho n from pi 1 of x. And I'll denote the surjection here. 2 pi 1 of Cn, which is isomorphic to Z, where we take the origin as the base point. As base. Then the product of the homomorphisms is a homomorphism. Sure, I'm willing to accept that. So rho of pi 1 of x gets mapped to the infinite product of Z of infinitely many copies of Z. P is rho is surjective, since for every sequence of integers we can construct a loop that wraps around kn times in each interval. This infinite composition of loops is certainly continuous at each time less than 1 and is continuous at time 1, since every neighborhood of the base point contains all but finitely many circles. Since pi 1 maps onto the uncountable group, it is uncountable. On the other hand, the fundamental group of a wedge sum of countably many circles is countably generated and hence countable. Pi 1 of x is actually far more complicated than this infinite product of Z. For one thing, it's not abelian, since the retraction to unions of CIs that collapses all the circles smaller than Cn induces a surjection from pi 1 of x to a free group on n generators. For a complete description of pi 1 of x, see a paper from 2000. It is a theorem of Sala in 1988 that for a locally path-connected compact metric space X, pi 1 of x is either finitely generated or uncountable. Interesting. This one made a lot more sense than the previous one. Yeah, so now applications. Cell or two cell complexes, sorry. So for the remainder of this section, we shall be interested in two-dimensional cell complexes, analyzing how the fundamental group is affected by attaching two cells. So according to an exercise at the end of this section, attaching cells of higher dimension has no effect on pi 1, so all of the interest lies in how two cells attach. Suppose we attach a collection of two cells. So suppose we attach a collection, two cells, E alpha 2 to a path connected space S via maps phi alpha from S1 to X, producing a space Y. If S naught is a base point of S1, then phi alpha determines a loop at phi alpha of S naught that we will call phi alpha. What? All right. So even though technically loops are maps, um, we're just going to treat it this way. For different alphas, the base points of these loops may not all coincide. To remedy this, pick a base point and a path. Um, so, so to create a common base point, pick x naught in x and gamma alpha in x from x naught to phi alpha of s naught um, for each alpha. Then phi alpha um, or gamma alpha, phi alpha, reverse gamma alpha is a loop at x naught. This loop may not be homotopic um, in X, but it will certainly be null homotopic after the cell is attached. So it may not be null homotopic in X until E2 is attached. Thus, the normal subgroup, thus N contained, or and normal subgroup pi 1 of x comma x naught, um, where n is generated by all of the loops, um, gamma alpha, phi alpha, gamma alpha, um, lies in the kernel of psi, where psi is a map from pi 1 x naught to pi 1 of y x naught, induced by the inclusion from x to y. Yeah, so because they're null homotopic. So proposition time. Um, the inclusion x to y induces a surge action pi 1 x naught to pi 1 of y naught with curve phi equal to n, i.e. pi 1 of y is isomorphic to pi 1 of x mod n. Um, oh wow. Well, it's another long proof. um, yeah. So let's expand. So proof. Um, let's expand y to a slightly larger space. Z, the deformation retracts onto y. So let z dr onto y. Um, Z is attained from Y um, by attaching rectangular strips. S alpha is equal to I cross I with I cross 0. Um, Attached to gamma alpha and I cross 1. So this is the left edge. This will be attached to the 2 cell that we're adding. And then all of the left edges. Wait, this is one. Sorry. Um, and all 0 and I identified together. The top edges of the strips are not attached to anything, and this allows us to deformation retract Z onto Y. So Hatcher has a picture that basically looks like if you have your 2 cell and you have your other 2 cell. This is then a point on its top is y alpha, which we're going to pick in the next paragraph, so don't worry about that just yet. Um, but then we're going to pick this point x naught, and we're going to have, some curve gamma attach like so. Do the same thing over here. And that's not at all clear that that's meant to be a taper. Okay, now hopefully that's more clear. Right? And this is gamma alpha, and then the top of it is S alpha. So the bottom curve that S alpha is built off of, I guess maybe I ought to switch these colors. So like, this is gamma alpha, and then this is S alpha. And so then, in each EF2, pick Y alpha not in the arc along which S alpha is attached. Let A be equal to Z minus the union over alpha of Y alpha. and let B equal to Z minus X. Then A deformation retracts onto X, and B is contractible. So A is this space minus the union of the Y alphas. A deformation retracts onto X because it splits apart. It creates like a hole. And then this hole gets attached down as a deformation retract. And B, which is Z minus X, which is Y, is contractible. Yes, I agree with that. I really love the picture here. This picture is great. So since B is contractible, pi 1 of B is equal to 0, and since pi 1 of B is 0, Van Kampen's theorem applied to the cover AB says that pi 1 of Z is isomorphic to pi 1 of A mod, um, okay, pi 1 of Z is isomorphic to pi 1 of A mod the normal subgroup generated by the image of the map on the intersection of A and B to pi 1 of A. So, I don't think we're going to use theta. Let theta be from pi 1 of A intersect B to pi 1 of A by, I'm guessing, the inclusion map. So then pi A mod the image of the intersection is isomorphic to Z, or pi 1 of Z. So it only remains to see that pi 1 of A intersect B, pi 1 of A intersect B is equal to the normal subgroup generated by the loops gamma alpha, phi alpha, gamma alpha closure. Or rather, by loops in the intersection of A and B homotopic to these loops. This can be shown by another application of Van Kampen's theorem, this time to the cover of A intersect B by the open sets. So let A and B be covered by A alpha is equal to A intersect B minus the union of beta not equal to alpha of beta 2 cells. So since A alpha deformation retracts onto S1 in the alpha 2 cell minus the point by contractibility, then pi 1 of A alpha is isomorphic to Z, generated by a loop homotopic to gamma alpha, phi alpha, gamma alpha, reverse. And the proof is complete. That actually, okay, that was a long proof, but that was not a bad proof. That was like one of the more reasonable ones. Um, the only thing here is that this is a little sketchy. But I'm willing to take it at face value. So as a first application, we compute the fundamental group of the orientable surface MG of genus G. So now consider MG of genus G has a cell structure of 1 0 cell, 2G 1 cells, um, and 1 2 cell. As we saw in chapter 0, um, the one skeleton is a wedge sum of 2G circles with fundamental group free on 2G generators. The 2 cells attached along the loop given by the product of the commutators of these generators. So pi1 of mg is isomorphic to the free group on A1, B1, AG, BG, such that the product of the commutators is equal to 1. And then a corollary of this is that pi1 of mg is not even homotopy equivalent, let alone homeomorphic, um, to pi1 of mh if g is not equal to h. Proof the abelianization of pi1 is the direct sum of 2g copies of z. So if mg is homotopy equivalent to mh, then pi1 of mg is isomorphic to pi1 of mh. Hence, the abelianizations of these groups are isomorphic, which implies g is equal to h. Yeah. Non-orientable surfaces can be treated in the same way. If we attach a 2 cell to the wedge sum of g circles by a word, we obtain a surface. For example, N1 is the real projective plane, the quotient of the two disks with antipodal points identified. Yeah. Okay. Um, so as a corollary, for every group G, there exists a two-dimensional cell complex xg with pi1 of xg isomorphic to G. And this just comes from the notion of free groups. Um, yeah. So now we're at the end of Van Kampen's theorem. We've been going for about an hour. Um, there's a lot of exercises that I think have to be done. Um, Not that I've looked at them, but based off of how I'm feeling right now, um, I feel like I need to do some exercises and So the next thing we're getting to is called covering spaces, and it doesn't look nearly as bad as this section. Um, and so part of me is really like, oh, I want to move on. I want to do this for the sake of like doing more. I don't really know. Um, I don't know if that's a good idea. Um, so let me just flip through a little bit and see if I feel like we can talk about kind of an intro to covering spaces. Okay, I think we can get through a little bit of this. And then what I will go ahead and do before we get into covering spaces, I'll pick out some problems um, that I'm going to do tonight after I end the recording. Um, and then, yeah. Um, so I'll say exercise one. Don't worry, I'll write these all up on the screen. Exercise one because it played a role in a proof that we did today. Um, exercise two is a good corollary of Van Kampen. Exercise three, I'm very curious about. Show that the complement of a finite set of points in Rn is simply connected if n is greater than or equal to 3. Um, I like number 4 because it looks not too easy, but decently easy. And maybe 5 as well. So 1, 2, 3, 4, 5. Um, 7 is good for constructing things. The cell complexes. Compute the fundamental obtained from 2 to array. Um, I don't like 8. I hate the whole torus thing. um, 9, maybe? A surface MG. CB, a circle that separates into two compact subsurfaces. Eh. Consider two arcs. Uh, 11 could be valuable. Um, 12 seems important. Um, 16. Um, so that the join of two non-empty spaces 21. Okay. Yeah, so then I'm happy with that. So exercises to do at home. 1 through 5, 7, 11, 12, 16, and 21. And then we'll move briefly on to covering spaces for like half an hour. So we've come to the second main topic of this chapter, covering spaces. We've in fact already encountered one example of a covering space in our calculation of pi 1 of the circle. This was the map with the helix above it, covering it. A number of things we provided for this covering space are valid for all covering spaces. This allows covering spaces to serve as a useful general tool for calculating fundamental groups. The connection between the fundamental group and covering spaces runs much deeper than this, and in many ways they can be regarded as two viewpoints towards the same thing. This means that the algebraic features of the fundamental group can often be translated into the geometric language of covering spaces. This is exemplified in one of the main results of this section, giving an exact correspondence between the various connected covering spaces of a given space and subgroups of pi 1 of x. This is strikingly reminiscent of Galois theory, with its correspondence between field extensions and subgroups of the Galois group. So let's begin with the definition. Oh, section 1.3, covering spaces. Definition: a covering space of X is a space X tilde with a map P, not rho, P from X tilde X, such that there exists an open cover U alpha of X with each alpha admitting P inverse of U alpha to be a disjoint union of open sets in X tilde each of which is homeomorphic by P to U alpha. It doesn't need to be non-empty, so P need not be surjective. So, like, in our example of the helix, maybe it'll be easier if I draw, like, an ellipse. Nope, an ellipse. You want to do something, do it yourself, I guess. So pretend like that's an ellipse. And then, we have have this getting mapped down by P, where we can take any cut of this and map it down like that. Um, and of course this is homeomorphic. Another example is the map. So this is example one. Then example two is consider P from S1 to S1 by P of Z is equal to Z to the N, where Z is a complex number such that the modulus of Z is 1 and Z greater than 0. Oh, this is also the helix example. Is Well, it's a three-space helix. It's analogous to the projection of the helix is to draw a circle wrapping around a cylinder n times, intersecting itself in n-1 points. The one has to imagine are not really intersections. For an alternative picture without this defect, embed S1 in the boundary torus of a solid torus S1 across the two disk so that it winds n times monotonically around the S1 factor without self-intersections. Then restrict the projection to the embedded circle. So this is a special case. This first example is a special case. Is for n equals 3. As a general theory, we'll show that these examples for n greater than or equal to 1, together with the helix example, exhaust all of the connected covering spaces of S1. There are many other disconnected covering spaces, such as n disjoint circles, each mapped homeomorphically onto S1, but these disconnected covering spaces are just disjoint unions of connected ones. We will usually restrict our attention to connected covering spaces as these contain the most interesting features. The covering spaces of the wedge sum of two circles form a remarkably rich family, illustrating the general theory concretely. Um, so, nope, wrong color. Consider S1 equals X. This is a graph with one vertex and two edges. Call them. So if this is A, then this is B. And we'll choose orientations for A and B, like so. Such a way that the local picture near each vertex is the same as an X. So there's an A edge oriented towards the vertex and an A edge oriented away towards the vertex. Wait. Let X tilde be any other graph with four edges meeting at the vertex. Suppose the edges of X tilde have been assigned labels. Right. We're going to call this a two-oriented graph. There's a table on the next page that I'm going to draw some. There's a small sample of the infinite variety of possible examples. Given a two-oriented map, a two-oriented graph We can construct P from x tilde to the wedge sum of the circle, sending all vertices of x to the vertex of x and each edge to the edge with the same label by a map that is a homeomorphism on the interior of the edge and preserves orientation. It's clear that the covering space condition is satisfied for P. The converse is also true, is that every covering space of X is a graph that inherits a 2 orientation from X. So prop every covering space X is a graph that inherits a 2 orientation from X. As the reader will discover by experimentation, it seems that every graph having 4 edges incident at each vertex can be 2 oriented. This can be proved for finite graphs. So a very classical and easily shown fact is that every finitely connected graph with an even number of edges incident at each vertex has an Eulerian circuit, a loop traversing each edge exactly once. If there are 4 edges at each vertex, then labeling the edges of an Eulerian circuit, alternatively A and B, produces a labeling with 2A and 2B edges at each vertex. The union of the A edges is then a collection of disjointed circles, as is the union of the B edges. Choosing orientations for all of these circles gives a 2 orientation. It's the theorem in graph theory that infinite graphs with 4 edges incident in each vertex can also be 2 oriented. There's also generalization to n-oriented graphs, which are the covering spaces of the wedge sum of n circles. Okay, so some covering spaces of S1, wedge S1. I'm going to draw both the interesting ones and the ones that I'm able to draw. So example, covering S1, wedge S1. So you have the basic one that was on the other page, and then this extension. Where this is B, and this is B, and this is A. What? And this is the free group A and B squared and BA, B inverse. There's also a circle, but I'm going to draw. No, yeah, I'll do the circle. So if you have a circle, and you have this base point, and you inscribe a triangle in the circle, where you have these outer edges are A, and these inner edges are B, 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 then this is the covering space determined by A cubed, B cubed, AB inverse, B inverse A. And if you reverse the direction of the interior arrows, you actually get a different presentation. There's a lot more of these. I think the most interesting one that I'm seeing in here, and I can't draw it, I definitely can't draw it. The most interesting is the free group on AB. So, A simply connected covering of X can be constructed in the following way. So, constructing simply connected covering space of X. Start with the open interval -1 to 1. Um, and let lambda be in 0 to 1/2. Adjoin 4 open segments of length to lambda at distance lambda from the ends of the previous segments and orthogonal to them. For the third stage, then this is a loop I equals 1 to n. And so this is 2 to the I. And what this ends up looking like, and I'm only going to draw like 3 stages of it. But if this is our thing, maybe we start with lambda of whatever length this is, but not 2, right? But then we can obtain this and then this. And then this, taking great care to make sure that things don't intersect. And so on and so forth. Um, Never mind that these are not very well done. Um, oh, and this is at distance lambda to the I minus 1. No, it's length to the lambda I plus 1. Yeah, there we go. Um, the union of these open segments is a graph with the vertices, the intersection points of horizontal and vertical segments, the edges, the subsegments between adjacent vertices. We label all the horizontal edges A oriented to the right and all of the vertical edges B oriented upwards. So all horizontal edges are equal to A with orientation right. Vertical is B with orientation up. This is called the universal cover of X. Because it is a covering space of every other connected covering space of X. um, is a covering space of 6. Um, um, yeah, there's some remarks in here. So, okay, a general fact that we'll prove is that the induced map pi star from pi 1 of x tilde with base x naught to pi 1 of x naught is always injective. Um, Changing the base point just changes like the conjugate subgroup of the original fundamental group. And then the main classification theorem for covering spaces says that by associating the subgroup p star of pi 1 of x tilde x naught to the covering space um, admits a one-to-one correspondence between all different connected covering spaces of X and the conjugacy classes of subgroups of pi 1 of x comma x naught. If one keeps track of the base point, then this is a one-to-one correspondence between covering spaces and actual subgroups, not just conjugacy classes. Of course, for these statements to make sense, one has to have a precise notion of when two covering spaces are the same or isomorphic. In the case at hand, an isomorphism between covering spaces of X is just a graph isomorphism that preserves the labeling and orientations of edges. Thus, covering spaces um, yeah, so you get isomorphisms that don't preserve base points and homeomorphic graphs that are not isomorphic subgroups. And you can also have subgroups which are isomorphic but not conjugate, although that seems like you would just conjugate. Maybe it's just non-trivially conjugate. Some of the covering spaces are preserved under automorphism of labelings. Yeah. So we'll pick up next time with lifting properties. Um, Depending on how much of these problems I get done, we might start tomorrow with some of these problems. Um, Otherwise, I'll just leave them to the viewer to do. Um, with the goal to just kind of maybe get up to the big theorem tomorrow. This is a really long section. um, I've got to say, this is not something I feel particularly passionate about. But, I mean, this is the last section, really, in the section on the fundamental group. I don't know. We'll see. Maybe I'll grow a passion for it. Either way, thank you all for watching, and I will see you tomorrow.